Okay, I would like to derive for you the period of a simple pendulum. And this is part of your curriculum. You need to be able to derive this on an AP test. And so let's start and see where we can go here. This is a pendulum. A simple pendulum has all the mass at the very end of it, and it's got a length L. And this is only going to work if the theta is very small. So our derivation depends on theta being very, very tiny. Okay, before we get started in this derivation, I just want to remind you that the relationship between A and X for simple harmonic motion is that A is equal to negative omega squared X, where omega is the square root of K over M. Okay, so, or at least it's equal to 2 pi over the period. Okay, so omega is 2 pi over the period, and A is equal to negative omega squared X. And if you can't remember where that came from, that's where, if we start with X equals A cosine omega t, and we take two derivatives, we get that. And notice how A and X compare. A and X are almost identical, aren't they? Boy, they're looking very close. They're both cosine omega t, except for A has an omega squared in it. So that's why we say that A is equal to negative, and it's negative too. So it's omega squared X. You see that? Okay. Well, let's take a look then at this. We're going to take a free body diagram of this. mg down. We got a tension this way. And we're going to break the mg into components. So we're going to have a part that's radial or along the rope or the string, and then a part that's tangential. So this part that's tangential, if that's theta, then this is theta too. That angle right there is theta as well. Can you think of this? You see how this vertical line is parallel to mg? It is. This line and that line are parallel. And you see this line coming through? I didn't draw that very straight, but that's a line going through two parallel lines. So these are alternate interior angles. So this is theta as well. That's theta. And if that's theta, and that's the hypotenuse, then this is mg sine of theta. That's acting like a restoring force. It's trying to restore it to its equilibrium. Equilibrium is right here. So it's trying to restore it to equilibrium. Okay, so I'm going to say A is equal to F net over M. We use that a lot, have you noticed? And so A is equal to, at least in the x direction, this direction, is going to be equal to mg sine of theta all over M. So A is equal to g sine of theta. Okay, now here's the thing. This is going to go through an angle, an arc like that. But if this is really tiny, that's almost a straight line. And I'm going to call this angle theta. And so I want you to see something. For very small, I'm going to call that a right angle. You might not think it's a right angle, and you'd be right if you didn't think it was a right angle, but it's pretty close to a right angle. It's very close. The smaller this is, the closer that is to a right angle. Okay. Well, so I also want you to see something. When you have two triangles, that if you have a triangle, I don't mean two triangles. If you have a triangle that has a really tiny angle to it, theta, so that's theta. This is the opposite side We'll call that op, and this is the adjacent side, and this is the hypotenuse. I want you to see that if theta is really tiny, then the tangent of theta, which is opposite over hypotenuse, that's pretty darn close to opposite over adjacent. Because the adjacent side and the hypotenuse are almost identical lengths. So this is the sine of theta. So tangent of theta is it's approximately equal to the sine of theta for small angles. This has a name. It's called a small angle approximation. Okay, so tangent of theta. So A is equal to G times the tangent of theta. Okay, now the tangent of theta is equal to the opposite side, so let's call that x, all over the hypotenuse, L. So A is equal to G times the tangent of theta, which is, the tangent of theta is x, it's x, opposite side over the hypotenuse, over L. Now I'm going to tack on a negative sign here because when x is negative, I need to do that to show you that when x is negative, when you're in the negative territory, then the A is positive. And when we're over here, when x is positive, A is the reverse. So I'm tacking on that negative sign. Okay, so it's negative gx over L. That's what A is. We're almost home here. So if A is equal to negative G over L, negative Gx over L, then what we can do is with this, that tells us that G over L must be omega squared. That's because A is equal to negative omega squared times x. A equals negative omega squared times x. So G over L is omega squared. And so omega must equal the square root of G over L for a pendulum. But omega is equal to 2 pi over the period. So I'm almost there. Solve for the period. The period is equal to 2 pi. Bring the period over here and bring this over on the other side, so you'd flip them. L over G. We're done. I know this is an approximation. This only works for small thetas. In fact, the smaller theta is, the better it will be. It's an approximation. Okay? So what did we do there? We used Newton's second law. To the net force in the x direction is mg sine of theta over m. And then you would just say A equals g sine of theta, because the m's cancel. And then you have to make that small order approximation. So you gotta take that sine and turn it into a tangent. And once you turn it into a tangent of theta, then you can say that tangent of theta is x over L, and then you're pretty much home free. All right. Thanks a lot.